Welcome to a demonstration of Microway's InfiniScope. The cluster we'll be looking at has 12 nodes. You can see that 6 of them are connected to one InfiniBand switch and 6 to another. There's one cable between them, between port 13 of each switch. Down at the bottom you see a strip chart showing the measured bandwidth for the last minute or so. Right now we're looking at the total over all the hosts, but we can look at individual ports if we want, like the HCA on the master node. The little colored squares show the instantaneous transmit bandwidth for each port. The size and color of the small squares represent the bandwidth according to the scale at the top. We'll be running a simple application to load the fabric. 12 nodes are paired up in 6 random pairs. Then each node in each pair sends 5 billion bytes to the other. At a gigabyte per second, that should take 5 seconds, and the total bandwidth should be 12 gigabytes per second. When everyone is done, we use a new set of random pairings, and repeat. You can see that we're not getting 12 gigabytes per second all the time. Sometimes we're getting 8 or even 4. Sometimes we get almost 12 gigabytes per second, and a pass takes about 5 seconds, but other times we get 5 seconds at 8 gigabytes per second, followed by 5 seconds at 4. And sometimes we get 15 seconds at 4 gigabytes per second. What's the problem? It's the single cable between the two switches. When we look at the bandwidth coming out of a port at one end of the cable, we see that usually it's 2 gigabytes per second. In other words, the link is saturated, so we're seeing contention. So let's see what happens when we hook up another cable between the switches. Performance is about the same, sometimes 11 or 11.5 gigabytes per second, and 5-second passes. Sometimes 10 or 15-second passes. The subnet manager recognizes the second cable, but there's no data going across it. What happened is that the subnet manager didn't update the forwarding tables in the InfiniBand switches. So we'll stop and restart the subnet manager to force it to recalculate and reload the forwarding tables. That's a little better. We're getting some traffic on the port 14 cable. There are more 5-second passes at over 11 gigabytes per second, but still some slower passes. Some 8-second passes at 8 gigabytes per second, and some about 7.5 seconds, starting at 10 gigabytes per second and finishing up at 4. Since the second cable improved things, let's try adding a third cable and restarting the subnet manager. That's much better. You can see that we are getting traffic across the port 15 cable, and almost all the passes are just over 5 seconds at close to 12 gigabytes per second. Let's see if we can make things even better by adding a fourth cable. Oops, we have a problem. Most of the passes are taking about 20 seconds and finishing up at just 1 gigabyte per second. The problem is with the new port 16 cable. The blinking yellow and black means that it came up at 1x lane width instead of the normal 4x. To get the connection up to 4x where it belongs, we'll reseat the connectors and restart the subnet manager. That's better. We're getting traffic across the fourth cable, and we can even find host-to-host paths that use that cable. For instance, the path from the master to node 12 uses that cable. The path is shown by the heavy black lines. The performance is okay, mostly in the 11 to 11.5 gigabyte per second range. There's not much contention, but it's really not much better than with 3 cables. What we figured out with Microway's InfiniScope is that for this cluster, 3 cables between the switches provide enough bandwidth for this application that loads the fabric heavily but randomly. We'll go back to 3 cables, see that we consistently get between 11 and 12 gigabytes per second, and conclude the demonstration.